In the last video, we looked at the connection between the force of gravity, which we know is an attractive force, so I'll go ahead and put a negative sign in there. Negative gmm over r squared, where m is the two masses and r is the distance, and then F is, of course, then the attractive force between those masses, and how that translated to a potential energy function, which is a function of r, which was negative gmm over r. Okay, well, we want to go one step further, and we don't want to just classify potential energy functions as they happen to be related to the force of gravity. We want to talk in general about potential energy and how its connection is to force. And so let's just look at u of x. And these are u of x problems, and I just want to do a pretty easy example. Let's just say I have some u of x, meaning a potential energy function that's a function of x, and we have some coordinate system. If we graph that, it would look something like this, right? It's just a quadratic, right? 40x squared. And let's say we knew the energy, the total energy of the system, let's say 160 joules. Let's go ahead and just graph 160. Okay, that's 160 joules. And this is graphing the potential energy as a function of x. And so when you look at it here, when x is equal to 2 at this point, all the energy, right, u of 2 would be 40 times 2 squared. All the energy is in potential. And if u is negative 2, all the energy will be potential. And then when you're here, let's say, well, there's no potential energy there. Just look at the graph or plug in 0 for x. Well, where'd the energy go? Well, it probably is then converted to kinetic. So we would know that the kinetic energy at that point was 160 joules. At any moment on this oscillation, the total energy has to be 160, and so it goes from 160 to down, and so like the kinetic energy would have to just kind of be this reverse parabola. That would have to look like this. Okay? This point right here, well, let's look at the force. And just like before, the force always is going to be the opposite of the derivative of u. Meaning if you're to the right here, what's the slope? It's the force is the opposite of the slope. I mean, du dx is the slope of the u graph versus x. So the slope here is positive, which means the force is opposite of a positive, so the force must be negative. Of course so, right? It would go this way, right? If you have a high potential, if you just let a ball roll down and go to a low potential. Over here, high potential would go low. Look at the slope over here. The slope is negative, so the opposite of the slope would be a positive force, which would direct it back this way. This point is a point of equilibrium. Equilibrium is a standard notation for talking about that the net force is equal to 0. No force there. And so if you put it to the right, it'd come back this way. If you put it to the left, it'd come back this way, because the force is always opposite this. And you think about, well, what does this mean? Well, for this particular function, take the derivative. The force as a function of x, the derivative of the opposite derivative of this will be negative 80x. And you're like, wait a second, I never even said that this was a spring, but now we can analyze it and say, this is just a spring. This equation is really just a 1/2 kx squared, just like we learned in our energy unit, for the elastic energy stored in a spring. And then the force is some negative kx. See how they're related? It's the exact same way. The force is the opposite derivative of that. And all of these things happen. The force is opposite the displacement. Move it to the right, force back to the left. This is a stable equilibrium. A stable equilibrium meaning there's a restoring force that makes the object tend to move back to there. But this is going to be true for all u of x's. I can get some u of x graph, and I can make it look whatever I want. So this is u, and this is x, and the graph could look like this. It could look like that. And let's say I gave it a total energy of only this, right? The energy total was negative 5 joules. So what would this object do? Well, wait a second. Can it have negative energy? And you're like, well, of course it can. The energy is going to be this combination of potential plus kinetic. Kinetic is always 0 or greater, but the potential energy can be negative because potential energy is all based on some reference point. So our total energy is here. And so if all of our energy was potential, I'd be there, and all of it was here, how much potential energy would I have something at a point like there? Well, at that point, your potential energy would be lower than 5. It'd be like negative 6, which would mean what? Well, it would mean your kinetic energy would have to be like 1, because we know the total energy has to be 5. And so this object would oscillate back and forth between here. This could be literally just a ball rolling on a ramp. This likely isn't a spring because it has this crazy work in it, but we know the potential energy is going to oscillate. It's bounded between that x value, we'll call that x1, and then it's bounded between x2. However, what if I gave it more energy? What if I gave it this amount of energy? And I gave it like negative 1 joules of total energy. Well, then it bounced back and forth between here and here. It'd have a different bounce set. Would have more energy. You gave it enough energy to overcome this hump and come down here. Well, now we have to classify these. See this point here? It's going to be different. This point is going to be unstable equilibrium. And think about why it's unstable. If you took a ball and you nudged it to the right here, it's going to go down that way. If you nudged it this way, it's going down this way. This point here and this point here are stable equilibriums, right? This one and this one are stable. If you're here and you're a ball and you roll to the right, the slope is positive, so the force is negative, and you're forced back to the left. And the same thing is here. You'd oscillate back and forth, slowly coming to a rest at this point. This way, oscillate back and forth, that's stable. This is unstable. Okay, it's like the same thing as a board. Take a board and hinge it here and move this thing. Won't. It's going to swing back and forth, and it's always going to come back to this equilibrium. Take a board and hinge it here. They're both in equilibrium now, but if you nudge this board, it's going to come crashing down. So this would be the version of unstable equilibrium, and hinging it at the top, meaning if the center of mass, if the center of mass is below the pivot, it's very stable. If the center of mass is above the pivot, then it's unstable, because if you give it a little nudge this way, there's going to be a torque, and that torque will continue to go away from it. These torques always are a restoring torque. Again, stable and unstable equilibrium points. Equilibrium always means a net force of 0. Unstable means you're going to move a little bit to the left, and you're going to even accelerate more to the left. Okay, and always the total energy is always the combination of both of those things. And so if you know the total energy is this, it can get this. It's going to gain kinetic, lose kinetic and gain potential, but still have some kinetic here. Gain some kinetic, and then all the kinetic goes back to potential. Could the object ever get up here? Well, if kinetic energy never can be negative, you'd never have enough potential energy if you only have -1 total. So this would be totally out of bounds unless you had more energy. You would oscillate from the red to the red and go back and forth. So the biggest connections are if I give you a u of x function, you should be able to take the derivative and find the force. You should be able to find equilibrium points by setting the force equal to 0. You should be able to decide based on a graph whether they're stable or unstable. If I give you the total energy, you have to know that the total energy is always a combination of both of those things, potential and kinetic. So if I give you potential, you can find kinetic, but if you know kinetic energy, then you can find the velocity at that moment. The potential energy is some function of x or some function of r if you're talking about gravity. If I give you an x value, you can find the potential. You certainly should be able to go the other way and say then that the potential energy is the negative accumulation of that force dx or dr, whatever variable you want. But the capital, I call them the capital U of x questions. I think there's about 4 free response questions that are in this category. because they're not necessarily gravity and they're not necessarily springs. They're just random U of X questions, and then you answer questions about equilibrium, net forces. Of course, if you can find the force at any moment, then you should be able to find the acceleration at that moment, because you know F equals ma, and so on. But typically these questions aren't too bad, but probably this is this, and obviously its corollary are probably the two key pieces.